Welcome to the Australian Water School, the home of demand-driven industry design training for the global water sector.
Hi, I'm Cray, and I'm glad to be with you today to kick off our 2022 webinar series. Today we're going to cover recreational hydraulics, but first let's have a look at the attendees from all around the world. Joining us from all time zones, looks like. Welcome to each one of you. I really do hope you enjoy today's presentation. I wanted to introduce to you our speakers today. We've got John Felton, Orly Gottlieb, Kurt Smithgall, and Shaw Mead coming to us from all over the planet. If you Google John Felton, Wikipedia will give you two choices. There's John Felton the assassin or John Felton the canoeist. So I hope we've grabbed the right one today. So maybe if each of you could just say good day, tell us where you're coming to us from, and maybe something about yourself, which one you've been doing longer, kayaking or hydraulic modeling, or I guess in Shaw's case, it's surfing or hydraulic modeling. So let's start with John.
Hi guys, sorry, I'll get that video thing sorted out for you ASAP. I'm obviously, as you can see on the screen there, a whitewater canoeist and kayaker, and I've been doing that for, well over 40 years. So it's predated everything. So my background is in whitewater kayaking. I'm a design director for Whitewater Parks International and full-time designing artificial whitewater courses.
Excellent. Over to you, Orly.
My name is Orly. I'm calling in from New York, USA this evening in my time zone, morning for a lot of you folks. And I was lucky to start whitewater kayaking the same semester that I took my first fluid mechanics class. So it's been about 11 years for both wonderful activities for me.
Over to you, Kurt.
Hi, I'm Kurt Smithgall. I'm coming to you from Colorado. And whitewater kayaking predates modeling for me by about 10 years. So I've been whitewater kayaking for 19 at this point.
Awesome. And then Shaw.
Hi there, I'm coming from Recreational, New Zealand, which is one of New Zealand's best surfing breaks. I've been surfing for almost 50 years now and modeling for about 30.
Excellent. All right. Well, thanks to all of our presenters for introducing yourselves. We'll get you to come back on individually in a few minutes and then all together for a live Q&A session at the end. But now that you know a little bit more about who we'll be hearing from today, let's introduce our topic. As you can see in the background here, we're going to be looking at some fun applications of hydraulic modeling and design. Now, we've chosen 3 activities to focus on today, rafting, surfing, and water slides, with some presenters who have combined those particular personal interests with their professional careers. One of the main questions that we want to answer for you today is when we move from 1D to 2D to 3D modeling, and when, despite all of the recent hardware and software advances, a physical scale model or a full-size model is still needed. Now, along the way, we want everyone to get a feel for the underlying hydraulic principles involved and to see how designers use those principles. So if I'm going to take a ride on this water slide, for instance, and end up at the bottom while water is pouring in from the middle here, I really want to know that the designer understands Archimedes and other background essentials to keep me safe. We'll also see some amazing new technology for modeling. At the end of today's presentation, we're actually going to get a special guest to come on who helped develop this movable endless water slide for the Discovery Channel, and we'll get to hear some of his experiences. Now, there were lots and lots of other random topics we could have chosen to present today. I put out a call a few weeks ago for people to submit some fun modeling applications. So as we kick off, since I see from the map that we've got people joining us from all around the world, all time zones, including ones that are in the wee hours of the morning, I thought I'd start with a CFD animation of your coffee cup. This is courtesy of our friends at Flow 3D. They'll show you here the differences between adding milk first or last and how you decide to stir it. So however you take your coffee, thanks for being with us today. Now, usually I've got a boring logo as my Zoom background. Since this is just for fun though today, I thought I'd turn off the filter and you can see what's actually behind my logo. And yes, I'm a grown man with a Lego collection, and you can also see my guitar. My interest in Legos and music might not combine as readily with hydraulic modeling as some of the other hobbies that we'll see here today. but I'll show how I try sometimes anyway to combine that. We're going to hear a lot about waves today, and music is really just waves too. In next month's webinar on the Froude number, in fact, we're going to hear about how the transition between subcritical and supercritical flow in water is actually analogous to sonic booms in the air. Since it's casual day today, I am wearing a t-shirt with an album cover that has waves, pulsar waves in this case. These ones are sometimes mistaken for sound waves or terrain. Now I've got a TikTok channel for water modeling, again just for fun, where you can hear some of the background music for these, and we put out a TikTok challenge a few weeks ago to turn these waveforms into terrain and then flood them. And since this webinar is, again, just for fun, I've included the winning entry here with some fluid dynamics right over the top. When I do courses, I'll grab some free terrain data for our tutorial models from random places that seem to align with my interests, but they'll have a purpose, I guess, and including this album cover here where I actually heard that this guy burned his mustache off in the photo shoot right here for the album cover, and we try to put out the fire in our tutorial model. Also, if you've ever wondered why Lloyd had to hold his boombox up so high in the air, this park is actually in a floodplain with a drainage channel, and we've taken out his Malibu with the flood wave here in this tutorial model. And by the way, while we're on the topic of music, we are looking into replacing some of the standard waiting room music that you hear as an intro. Over the last few years, we've used the same one. I have heard rumors that some of our attendees have musical skills. So if you're in the water space and you have some original music that you'd like to share, go ahead and send it across to us, and you may get a captive audience of several hundred listeners as they wait to join these webinars. And we will credit you accordingly, of course. So there are lots of ways to have fun with water modeling and design. I can't say I've used my Lego building skills in my professional career, but here's someone who did with this model of the Hoover Dam. I also wanted to highlight a few other random runner-ups that we considered as we narrowed down our presenters for today. Some of you have listed fishing as an interest in the comments, for instance, and so the salmon cannon that we featured in last month's webinar might help you shoot some fish into your favorite recreational fishing spot. Or if you're into amusement parks, Coney Island here is definitely a recreational area, and just like many resorts these days, there are engineers using hydraulic principles to rebuild or nourish those beaches. If you like playgrounds or sports, just think of some of the hydraulic principles that designers had to use to make these fountains and animations. Likewise, swimming pool designers have to use some of their skills and they better know their stuff too. If scuba diving is one of your interests, just think of the phenomenal hydrostatic pressures that you'd have to design for to be able to wave at someone through that window if you're 50 meters down in this deep dive pool. There are some hydraulic designers who get to use their skills for entertainment purposes, like you can see in these fountains, which take advantages of some of the principles of laminar flow and turbulence. There are some modelers who just put things together, well, just for fun. And here are a few examples in anticipation of the upcoming Brisbane Olympics from Water Modeling Solutions. They always seem to like to put ducks in their models that they feature on their LinkedIn posts. And speaking of ducks, you can see here the slow-mo guys. I'll speed this up. They're slow-mo, and you can see here that they put some ducks in a pool, and this is where the waves in a circle, they start out in a circle and then they concentrate into a single point, and then you get some crazy results here. I don't know if you've ever seen a vertical hydraulic jump. Laminar flow is going turbulent where it hits this obstruction. The same thing happens in your sink in reverse. I'll get myself out of the way there so you can see laminar flow hitting obstruction and going into a wave form. Now, there are lots of our attendees with a flood control background. Here is recreational overlap. The architect of the skate park is actually a skater himself, and now a hydraulic designer too, because these actually double as detention basins for flood control projects. So back to the interests of our, the three interests that our presenters will cover. Here, we're going to talk about hydraulic jumps and Froude numbers. You can see the transition for flow here, and we'll also address other relevant aspects of the design process, like public safety and how design principles are applied to make recreational features, both fun and safe. Now, things that are fun can very quickly turn into a hospital visit, or worse if the designers aren't on top of their game, as you can see here. Now, we have got a ton of information for you, but our time is limited. So for each of the examples we're covering here today, I've got additional papers and videos and other links that I've posted on an accompanying website. It's called surfacewater.biz/fun. Now, on that website, I've got additional papers and videos and other links that relate to what we're talking about today, and some detailed courses, some links to detailed courses covering the Froude number, wave forces, and other topics. And these are available for registration at the Australian Water School's website. So today we are going to be hearing from some people who are lucky enough to be able to use their passions in their careers. First off the bat, I'm absolutely thrilled to be able to hand over to our next presenter. When we were planning this webinar, I started scouring the globe trying to find someone who had worked on one of the Olympic whitewater courses. Little did I know, right here in Australia, we've got the jackpot where we were able to find the lead designer on not just one, but 5 of the last Olympic courses. And not only that, he is an Olympian himself. So with that introduction, over to you, John.
Excellent. Thank you, guys. I'm just going to give you a sort of a bit of a walkthrough of how we use modelling. And I'm going to use an Olympic example so that you can see really what we did at the last Tokyo Games. And we'll have a bit of a video on the Rio Games that we did as well. That was an interesting vertical jump that you looked at there, Craig. If you look behind me there on if you see my video there, we've got the first raftable waterfall that we modelled, and it's in Auckland in New Zealand. And that's, really we're modelling that so we don't create those retentive sort of hydraulics, and we keep people safe as they go through them. And the same thing happens when we're doing our whitewater courses as well. So if I step through a little bit to give you some background on this, look, the purpose we use this for is really to inform the detailed design phase. We provide a basis for any necessary revisions, and then we establish an initially compliant obstacle configuration. And what I mean by compliant is that for the International Olympic Committee and the International Federation, they agree that obstacle configuration to create that whitewater will comply with their requirements. The other side of that is satisfying those technical specifications for hydraulic performance. We spend a lot of time mitigating energy loss, and with somewhere like Tokyo, it's 4.5 meters of head with 12 cubic meters of flow. So over that amount of time, and it's a 250 meter length of channel, we've got to be really careful that we don't lose too much energy in any one place. So it's really important that we do the modelling right. Otherwise, the detailed design doesn't deliver on what we're expecting. So we look at things like specified depths and flows, and in the eddies, and also in the middle of the flow, and then we optimise those velocities around that. So I think that Orly and Kurt are going to cover this a little bit better, but really we have to create our modelling parameters from the Froude simultube scaling. And the model itself we've done from a 1 to 13 scale. And I guess you can see on screen there that there's other scaling that we need to do to make sure that we've got the model at the right scale from an area, velocity and discharge. So looking down at the full course, it's 250 meters. So our model was just under 20 meters long. And our flow rate at 12 cubic meters is just over sort of 19 liters per second. So if we move through that, one of the things is that we have to move our course design there on the left into the physical scale model. So those scaling parameters are incredibly important. And then the third part we do when we've got the physical scale right is that we have to create a whitewater language, if you like, to describe what's actually happening in that channel. So if you look at this, I mean, everything in the channel where we sort of describe the whitewater, you see the blocks here, and the different colours actually show the different heights of those blocks. So these one around sort of the 26 metre mark, those green ones are 1.5 metres high, and those light or aqua ones are 0.5 metre high. And so you'll see there it tells us exactly when we go to put these blocks in, and they all come in 25 or 250 millimeter increments. We know exactly the height to build there. The other side of it is you'll see these numbers here. The arrows gives the direction of the flow. So the flow is downstream. It's from the right to the left on your screen. So the upstream in the eddies here, these blue arrows here, the blue numbers gives us a velocity number, and it's plus or minus sort of variation there. And the red numbers gives us a depth, plus or minus variation, and the dot is the point that it's measured. Now, we have over 70 points of measurement within the channel. And this is really important for us because we measure this also in the constructed channel, and then we compare that with the model. And those inputs actually allow us to make improvements in the way that we do our modeling. So when we're looking at this, where the parameters that we have to look at is minimum depth is the 600 millimeters at any space throughout the channel. The minimum depth in the eddies is 1 meter. The minimum velocity upstream in those channels is 1.5 meters. And we really have to make sure that we don't have any overtopping of the channel, that the surging is minimal, and that the whitewater is suitable from an Olympic perspective. One of the real sort of, I guess, limitations of the physical modelling is we can't get the air entrainment. So there's a little bit of experience that we need for that, because that, as you know, will create a little bit higher hydraulic jump, a bit more retentive, and also slow the water in different parts. We then go on to the design from the scale drawings, and we've got a bit of a construction tolerance on the laboratory floor of plus or minus 2%. We build it out of plywood, and we use sort of brick supports where we can. And then we spend a lot of time making sure we don't have any leaks and waterproofing it. As we build into the channel itself, we use the extruded polystyrene, and then we cover that with steel plates so we can move the obstacles around, and which we have magnets in. So if I start the video here, we've got it in partnership with the Czech Technical University, and basically it's just a little video on how we actually put that together. But the main thing here is to see if we can make sure that we can have this scale model conform to what we need in reality. So as we said, it's just over 19 litres per second. It's going to give us the 12 cubic metres. And that then allows us to actually use the adjustable components of the obstacles. And this was one of the things we had to actually come up with. How do we quickly move things so that we can change things in real time? So we've created these real scale models of obstacles. We've put magnets in them. We're able to then place them in the water on the sheet metal. And in real time, we can actually pick them up and move them around so that we can create the hydraulic conditions we need. Now, if we find we don't have the optimal hydraulic conditions, then it's very easy just to move those obstacles around and create something different. So this has sped up the hydraulic modelling quite significantly. Then what was important when we did the measurements is that we then come back and then we're able to integrate, I guess, that into our future modelling. And this allows us then to go from a model into reality as closely as possible. And I think we're pretty good because we control everything in these models up to around 90% of where we should be. The last sort of 10%, we need to get in and move it because we can't, as I said before, we can't control that entrained air. We've got a little bit of different sort of friction coefficient. So we're looking at sort of the variables here, and we're looking at sort of these impeller flow measurements, and they equate really very, very well with what we do in live situations. And this is, I guess, an idea of, that computer, that sort of language overlaid on top of the model itself, which really then we're doing is overlaying that back onto the real whitewater that we've created. So as it says there, it's always good to have kids involved, and they always like to play in the water and take their little boats in, but that's, I guess, a nice thing that the university has been able to do. The next part of this is at the bottom of the Tokyo course, we have an easy river, and I think you've probably seen a number of these as lazy rivers in different situations. We've had to take that and really change the concept on that. We've added within that sort of 15 different pumps. Really, each one is about 0.2 of a cubic metre per second. So it's a big, and we get flows between 1 metre per second and 2 metre per second in different things. But the issue is this outside lane is the lane of the whitewater course, and its integration of this course into that easy river is where we use the fluent model to do that. We can't really do that in the physical model. With CFD modelling, that allows us to do that. And this is sort of the main thing. And the other place we use it is down sort of into the pumps. But I think Orly and Kurt are going to go through that in a lot more detail. But that gives you an example, I guess, of using hydraulic modelling on the ground and in real situation.
Awesome. Thanks, John. Thanks so much for coming on, and we look forward to having you on as long as we can have you for the Q&A sessions. So keep those Q&A questions coming in the background for everyone. With that, we'll turn it over to Orly if you want to start sharing your screen. Thanks.
Awesome. That was a very cool video to get to see how you use physical modeling to make your courses as wonderful as they are. So my colleague Kurt and I are going to talk through some basic design tools that are commonly used to design whitewater recreational features. If you're designing an Olympic course like John is, you're probably going to need to do as much as you can before you get out there to build it. And that includes going all the way up to using a physical model. For some projects that can be financially prohibitive because they're a little more expensive to do. So there's a range of tools out there, from starting with hand calculations and spreadsheets to doing computational models, which John showed a few screenshots of, and physical models as well. I was lucky enough back in my hometown in New Hampshire to get to work on a smaller community project, and we didn't have the budget to go build a physical model. We just had to use the tools that were within our project budget to make the project work. But it's important to know from the design side that there's all these different tools out there that can help you get from point A to your finished product. John mentioned computer models can be really useful to help design these. Some pluses of using a computational model. This screenshot shows velocity on the surface after a run. Kurt did this a couple weeks ago, I think. Doing a 3D computational model can be really useful for understanding what the velocities would be anywhere within your flow area. That can be a little bit difficult to get that much detail out of the physical model because of how much instrumentation that takes to get every single point within your flow field. So a CFD model like this, you can grab data from any slice, vertical, horizontal, and get a pretty good idea of what flows you might expect. It's a really good tool for doing some rapid prototyping to see what might change under various flow conditions or if you change the geometry. But there's going to be uncertainty related to the model. The computer models don't do a great job accurately representing aeration. We'll show some photos of a wave in a minute, and you'll see the white part of the white water is actually air mixed in with the water. So that doesn't come through really well in the computational models. And there's also scale dependence within the model grid that you set up. So you have to really think carefully about how you're setting this up to make sure it's going to accurately present what you might expect to see in the field. The next step up, if you have the budget for it, is to do a physical model. These are really fun projects to get to work on, and it's going to give you a more accurate idea of what things are going to look like in the field when you go to construct. John mentioned that they do a lot of work and feedback from seeing, okay, this is what it looked like in the field, and you can go back and fine tune your physical model. And it's really nice to have all of that information so that you can design better as you move forward. The air bubbles are still going to be tricky to scale in the physical model. So it's not going to be exactly perfect, but it's a really good tool to give you more confidence in your design before you go to build. So John mentioned when you're setting up your physical model, it's really important that you think carefully about the physics and that you're accurately representing them at a smaller scale so that your model will be as realistic as possible. For a free surface model, which means that the top of the water is open to the air, the most important thing to consider is matching the Froude number. The Froude number is a dimensionless parameter, and I'm showing here, it's defined for shallow water waves, so like in a river, what John is showing on his previous video. The Froude number is the ratio of the velocity divided by the wave celerity. The wave celerity is, what that means is how fast does a water wave travel across the surface of the water. So this picture on the left, you can see me in my kayak. We've got some nice, fast green water coming across from right to left in this picture. That fast water goes over some sort of rock. It picks up some speed as it comes down, and then it hits this pool underneath and pops up and creates this slower section where the wave forms. And that wave will be right there at a certain flow rate, and it can be a really fun thing to go play on all day. Over on the bottom right here, you can see Kurt in a much bigger wave, a little more adventurous than I am. Something that's really important to think about with all these different waves that can form out there. Not all hydraulic jumps are going to be fun. John mentioned that they designed this really cool plunging waterfall that you can go over in a raft, and they had to be really careful modeling it to make sure that they didn't get a dangerous hydraulic at the bottom. So just big picture, what the difference might be is that, you could have in one spot or, a similar geometry, you could wind up with a nice fluffy wave that sits right at the top of the water column with mostly the water shooting across underneath. So if you flip over or get out of control, the river right underneath will help carry you downstream and you won't get stuck there. But you could also set up a hydraulic jump or a wave where the recirculation goes a lot deeper into the water column. And if you get out of control or wind up out of your boat swimming, you could be caught in a much larger recirculating current that can be very dangerous. So it's really important to take all of that into consideration when you're designing these things. So let's look at what this looks like in the real world. So you can see up on the right side of my screen, there's kind of slower water moving across. You can see the speed picks up a little bit going over. There's a rock underneath. It goes over the rock, plunges down into this pool, and then we get this recirculating region where the wave, the water right at the top of this wave you can see is actually moving upstream, and it forms this standing wave right here. That's really fun. Let's go on to the next. I'm going to hand it off to my slightly more adventurous colleague, Kurt. Thank you.
So in thinking about hydraulic jumps, if you pull open a textbook, you'll get these nice schematics showing little arrows. And it's hard to really understand what's going on. So when thinking about whitewater or designing these features, it's really useful to understand what's happening in hydraulic jumps. So for a whitewater feature or kind of a drop structure, you could approximate that as a backward facing step so that you can compare and contrast different flow patterns, because hydraulic jumps exist on a spectrum, and there are, say, these 5 stable different flow structures that exist. And these come from literature. These have been studied in physical models as well as numerical models. So I think it's useful to kind of look through each one because they each have different safety and recreational impacts. So starting off with what's called the minimum B jump. This is where you have a supercritical jet that comes in from the left, and that plunges all the way to the bed and creates this big aerated recirculation region. Now, from a safety concern, this is what you would see at like a low head dam, where you have this roller that can then entrap people because you just get stuck in that recirculation region. And this is generally a function of like a lower tailwater height, because that supercritical jet just plunges in and goes all the way to the bed. As you start to increase the tailwater height for a given fluid number, the structure of this jump will change. And you'll see the supercritical jet now starts deflecting upward a little bit. You still have this aerated recirculation region that's very chaotic. But in some cases for kayaking, you do play in these recirculation regions. So it's quite hard to determine what's safe or what's not, because these flow structures are scale independent. But from a retentiveness and safety standpoint, that is dependent on scale of that recirculation region. So as you continue to increase the tailwater height, there's a point where that surface recirculation region just starts to get washed out, and you get this undulating hydraulic jump. Like on natural rivers, this would be a wave train, or what you would see kind of propagating, undulating downstream. And these are very safe because you don't have that recirculation region. You just have this nice supercritical jet, makes a fun little ride. So these are good for safety, but for recreation, you still get a wave, but it's not as big as it could be. So if you continue to increase the tailwater, you'll end up with what's called a wave jump. And this is a pretty extreme example because the wave height is several multiples of the flow depth. So it's pretty impressive to be able to get it to stand up that high. And you can see through the animation, you end up getting a submerged recirculation region directly under the wave. And this is what stabilizes the wave and props it up. Now, there is also a safety concern with something like this because you now have this secondary hydraulic with a large aerated recirculation region behind it. And as you increase the water tailwater height even further, you'll end up with this A jump. So in this case, the supercritical jet comes in, but it gets deflected upward to create this smaller recirculation region. Now, these are, like in whitewater sense, you would call this like a wave hole. So these are commonly played in, but there can be a point where there may be a safety concern. So when you look at these as the full spectrum, you start out with a minimum B jump, and then as you continue to increase the tailwater height, it transitioned into a B jump. When the recirculation region washes out, you end up with an undulator jump. And then when you increase it further, you end up with a wave jump, and then even higher is the A jump. And past that, then it just becomes a submerged hydraulic jump. So this is for a given fluid number. When you expand this out to a larger variable space, you can look at different fluid numbers and different tailwater heights to kind of get this bigger picture scenario of where hydraulic jumps like to exist. So for like a whitewater park, if you want to design a surf wave, you want to make sure you're in this undulator to wave jump region to start, because you can only do so much with like kickers or fine tuning things. If you're not in the right hydraulic parameters to start with, you'll be fighting a losing cause. And same thing for safety concerns. If you know what your fluid number's at and what your tailwater's at, if it becomes like a B jump or something, you can increase that tailwater height to try and get it to wash out a little more. So then when thinking about specific projects, whitewater is pretty tricky because for like a dam, if you're designing a dam, you'll have this rating curve and that'll be your design criteria. But with whitewater, it's quite subjective. And like to John's case, a lot of the successful whitewater people are also whitewater designers, are also whitewater paddlers or surfers. You have that real world experience with the whitewater itself, not just studying it from an engineering standpoint. And these projects are also difficult because you need to balance both recreational value along with safety. But then when working on natural rivers, you also have ecological function, and fish passage often becomes a concern when designing parks like these. And then similar to this photo, there can be considerable construction uncertainty when designing these grouted boulder structures. The pump parks like the Olympic ones, luckily those are smooth concrete and your tolerances are a lot smaller. So the uncertainty is a lot more manageable compared to when you're working with large boulders where there's a lot more variability in material. One last kind of plug that's kind of neat for CFD is you can also use CFD to visualize like you would with a physical model. And this is just a little extra step where you can take the model outputs and render them. This was done in Blender. But this gives you a nice tool to show what a given feature would look like without having to go so far as, say, a physical model or building it. So you can prototype with a bit more realistic, as well as get some marketing aspects. So here are two references from the works I cited. And here's just a quick plug for different resources from Alden. And thanks.
Awesome. Now we'll turn over to Shaw. It's going from the, we're going to go from whitewater into surfing. So over to you, Shaw, if you want to share your screen.
Okay. Yep. So heading across the surfing, now those were really interesting in understanding the applications with the different models. I'm going to go through quite a few slides and quite a few fast, really, because I've actually been involved in the wave pool research since 1999. There's a few of the projects there, not all of them, and not all of them have been built. But you know, really, my background, my PhD was in surf science, and so it's really been about applying the surf science through numerical models, and that's been used in through design, through the management of so design of artificial surf breaks, pools, so both in the sea and on land, but then also in the management of surfing breaks and also the protection, so used through a variety of things. One of the things, so as I said, I'll jump through these ones. We've been doing a lot since 1999 so far, and so my images and some of the videos are pretty grainy. Some of them are old, some of them are new, some of them the latest stuff we're working on. So back on that other slide, actually I can go back up. So the G wave, that's picking up Greg Webber's designs, and then Endless Surf is like a Waco type product in Canada, the biggest company in the world that does surf parks. They're located in Canada. And then the Westlake surf pool. So we're looking at everything from plow designs, very like a Kelly Slater type of pool or surf ranch. Then a caisson design using air to push up the water, and a flat type design. And so, whoops, gone too far up. So we've been involved in designing the wave generators. So these kind of things. So, and then use the numerical modeling for the design. And then physical modeling is the end product. And one of the things Craig was talking about is, you know, when are you using your 1D, your 2D, and your 3D models, and when is it time to jump to a physical model? So there's been some, we've got plenty of good results over the years. And that is the normal process for us. We will start in, well, I'm calling these one-dimensional, but they're, you know, slices through the model or in one dimension. So this one here we're looking at, and both of these ones we're looking at generator design in this case. And the critical issues really were is turbulence around through here. So this is a plunger type design, or same as a caisson, where you're lifting air up and down over here and pushing out. So these dimensions and the morphology of the generator here to fire that wave up against the pool are really important. So minimizing turbulence and then getting that right aspect of surfability. So I know I haven't got my long, so I probably should have put a slide in on surf science, but really what we're trying to understand and bring together are the three parameters of wave height, the wave peel angle, how fast the wave peels, and the breaking intensity. That's how hollow those waves are. So then next in 2D, we'll often use the like a boost nest type model. This is going really fast. It's actually a 500-meter pool, but using that kind of thing, we can stop that, investigate at any time, take transits through, look at wave heights, put on overlay the braking patterns to look at peel angles, and also through taking slices, we can look at what the orthogonal gradient is. That's the gradient that the waves are traveling up, so that we can work out how intense they're braking. Our next stage, we go into the 3D, and I'll loop back to that at the end. Just, a lot of it is mostly for visualization. We have been looking in the last few years at wave-driven currents, aspects like that. And really, there are some problems that we hit. But finally, we get to the physical modeling, and there are a lot of things that we have to look at in physical modeling. As we heard before, it's very hard scaling things like air bubbles, and also actually getting a real handle on what the wave-driven currents are. That's one of the biggest issues for us. When you're driving all that energy into a small area, you start to really set up the currents. And while you want them in say, your kayaking, you don't want them in your surf pool. Again, if we look at a project from back in the early 2000s, this was where we designed our own generators for it. We were originally looking at caissons, and I'll show you why we went away from them. But first in 1D, and then jumping into 3D to then get, and these actual generators, Auckland University bought them off us about 12 years ago, and I understand that they're still working. Then we're using the boost nest type models. Boost nest models are actually very good for looking at your reflections and your wave-driven currents. We often use them. A lot of my work is in hydrodynamic modeling and sediment transport modeling. So you use your boost nest and looking at wave agitation, say within a port structure. And then things like looking at the elements that we're constructing them out of. And this was to do with a moving floor. We actually, this is a third party did that. It's not my own modeling, but it was very useful to get us to understand how they all work together. So from those models, we then get into the physical modeling and really want to validate those surfing kind of aspects, how hollow the wave is, how fast is it peeling, and how that fits into skill levels for surfers. One of the big problems, like I said, is the wave-driven currents. So we were looking with much easier back then, before we really had the CFD models working very well, didn't have the computer capacity to get them going, using the physical modeling to look at these flow return systems to take those currents out of a pool. In this particular project, we actually went, that one there, we're looking at a 1 in 10 scale model in a warehouse, and we went all to a 1 in 1 scale model, and this was in Florida. And these are the big caissons, the air-driven ones, and I will show you on here why we went away from this type of thing and why they weren't actually used way back. This was 2006. You can see a guy on the side of the pool. So you see the height, the wave comes up probably about 8 foot, but unfortunately there's no back to the wave. So by the time it propagates away, we lose half the wave height. But very useful getting a full scale model and learning that kind of thing. So a nice spitting barrel going through there. And I think Nick there, even in that tiny little test pool, was getting inside it. Another one we looked at, and this is just a continuous wave, a New Zealand project that never got off the ground. So this generator moves from side to side and generates a wave in both directions. We had to modify that generation, but looking at what our issues it would be when we're trying to do that and spin that up. So getting our initial work from the numerical models and then going into the physical modeling. And thing about physical modeling, and it's similar with the numerical modeling, but you just end up with screeds and screeds of data, which you want to, you have to analyze. And what we're looking at here, this whole continuous pool, is because you're reinforcing the wave, by about the 10th, 11th wave, you can reduce your energy input and have a wave that goes round and round the pool. It's more of a fun wave rather than surfing. And you see here how we're getting it up steeper and steeper. if we break the pool, the waves, then we're moving water particles and we make a whirlpool that won't work. So we're looking for that critical point where it's standing up but not breaking. And so there's some really exciting stuff actually coming out of the Weber design stuff we're working on, but we are under non-disclosure agreement with that one. But here, just looking at the endless surf. So we're mostly using SPH, dual physics, using top of the range graphic cards to drive the modeling. And due to COVID and travel restrictions and lockdown, we've been working and collaborating with Endless Surf, or it's Whitewater, in Canada and France. And so doing all our work just in 3D modeling, we haven't had a chance to do a physical model, but we've been able to look at each of the aspects. So what's the break-in intensity, peel angles by plotting you can see the wave coming in the broken areas. So you can measure the peel angle, which is the area between the crest and the broken whitewater. Looking at overtopping. So we're trying to get the currents out of the pool. So, but what kind of turbulence is that creating in our flow return system? Things like reflections, how we're getting rid of them, and they're a combination of bouncing off the wall and this overtopping we see here. And even looking then getting into wave-driven currents and how long they take to dissipate. So how many waves can we have in a set when we drive them, and what are the best ways to get rid of them? Be cautious there. Just my last point is that we're getting into this to try and optimize your computer time. These are modeling water particles. And there's been a rule of thumb around for a long time that you can go to 10% of your wave height in a water pump particle is all okay. We've done a lot of tests and done a lot of investigations and trying to find out reviews, but we find changing water particle size will change your wave height, and it has a big impact on your wave-driven currents. So we still don't know what is real when we're using these models without actually having a physical model to validate them. And that's it from me. Thank you.
Excellent. Thanks, Shaw. That's fascinating. If you want to put anything into the Q&A for all attendees, ask those questions. We've got some great answers on there already if you want to check that. We're going to now just take a real quick look at some water slides, just a couple of minutes here, but we will go past the hour. If you need to run, you'll be able to tune in on the YouTube recording later on. So I just wanted to share here a couple of things about water slides, and the question that came up that we put onto the webinar registration page was whether you've ever ridden a water slide with an integrated Archimedean spiral. And that's what we've got here on this animation. You can see the equations behind an Archimedean spiral, and again, this kind of feeds into what we're talking about with some of the courses coming up. We want to take things that are this complex, even for a simple circle, and imagine what this would look like for the actual constructed project here, and really simplify things and explain these terms in some of these courses coming up. But what I wanted to show you here as well, this is the one that we were just looking at. That's a German design for a rotating water slide from Wiegand. This right here is an American design, as we'll hear now, I think from Dennis a little bit. And then I wanted to show you a rotating water slide here in Australia. So these hills hoists, we've got one of these in our backyard, and when the Australians on Australia Day here get together and do a rotating water slide, well, this is what it looks like. So Dennis, if you've got your audio working, if you could come on.
Can you hear me okay?
Yep, well, I can hear you just fine. Excellent. So what I'll do here is put on the video, hopefully you can see this, of this thing that you were working on. If you could just give us a brief description for a couple minutes of what this was, and then we'll dive into our Q&A.
Right. So in 2008, this is the Backyard Waterslide Simulator episode of the show Prototype This, and it was put on by the Discovery Channel, and the production company was actually Beyond Productions out of Sydney, Australia, same production company that did Mythbusters. Well, I was invited to help out with the hydraulic controls on this particular show. They were having a little trouble, and this is a very massive build. They have a 6,000-pound wheel that is lifted up and down 1.5 meters. It's tilted back and forth 1.5 or 15 degrees, and it can spin at up to about 14 to 15 RPM. And what happens is that they have a computer-generated water slide of whatever geometry they want to do, of whatever length they want, and they project that water slide, that computer-generated water slide, into the tunnel right there. And what we did, or actually Andrew Brooks did, is he extracted, that's him right there with the white mohawk, and by the way, he is Australian, and also an MIT roboticist. What he did is he extracted the motion data from the video, and then I took that data and I created cubic splines for the 5 axes of control that is being controlled right there on the water slide. And we basically created a ride. And one of the benefits is that you could actually do physical modeling of a very large system. We had very precise computer control of that physical model before and we could test that. You can actually see the simulated water slide down there on the lower right. We could control that, we could run it, we could see what it felt like before the complete physical model was built. So all of that was done using servo hydraulics, and that's all hard real-time control of those servo hydraulics. I guess the point of this is that you can apply computer control to some reasonably large physical models and get a better feel for what your results are going to be before you commit to building the entire thing. And of course, this doesn't work in all scenarios, but in some cases it is applicable.
Awesome. Now, thanks so much. We're glad that we were able to get you on here, having worked on this one. I saw this, just a clip on YouTube of this, and I thought that was awesome. If we can get all the other presenters to turn their screens on, I'll stop the share here, and we'll all come back on then. And I wanted to just have everybody answer at least one question that you've hit from the Q&A. And what I'll do is I'll start out with a couple of the ones that that John Felton had already answered, and he had to run, unfortunately. But somebody had mentioned that the Penrith course that he designed is over 20 years old, and asked if he's got some lessons learned in the meantime. And he said, yeah. With energy costs and things like that, we can actually design things much more efficiently now and get less head loss. And so it's cheaper to run per hour for the more recent courses. And so that one's considered a granddaddy. The other one that I love this answer that Bill asked him, do you get to ride these things yourself? And he says he's always the first down. So that's the standard. So have a look in there if you're interested in the responses on the instrumentation. He's got some answers there to some of the questions that people have posed. Now, over to you. Let's start with Orly. I know you've been answering some questions in the background. Wanted to talk a little bit about safety, and I know you answered a question about safety. So maybe if we could have you comment on that one and repeat the question, since people watching the recording won't see that in the background.
Absolutely. So Tony asked about low head dams, which can produce dangerous hydraulics immediately downstream of the dam. And asked if they could be redesigned to avoid those dangerous conditions. And he's absolutely correct. Depending on the site conditions and whether that dam may not still even be in use, that's a great opportunity to modify that site to remove the safety hazard and potentially provide enhanced recreation and enhanced passage for fish and other wildlife that can also use that site with the low head dam hazard removed and modified. So yeah, thank you.
Yeah, thanks for that. Kurt, I saw you answered a question about safety as well. Can you maybe state what that question was and what you answered?
Right. So the question is, how common are whitewater safety incidents, and how often do these relate to design issues? And that's a good one. Unfortunately, on natural rivers, there continue to be whitewater kayaking accidents just because it's an uncontrolled environment. But for constructed features, these are quite rare. And if there are any safety concerns, typically immediately after construction, they'll be identified and try to come up with a plan to fix them. So if there are any safety concerns, chances are they'll be fixed if they're man-made just due to liability.
Thanks. Awesome. Now, we get a lot of 1D modelers, 2D modelers, a few 3D modelers on these calls. The spacing for grids is very different when we start talking about CFD models. Kurt, I saw that you had an answer.
Sure. So the question was, how do you find a fine mesh, 6-inch or 3-inch or 1-inch? And this is a tough statement because you can't really give a blanket statement on what a required mesh size is because they tend to be case dependent. So specifically for that kind of final rendered animation I show, the final fine mesh resolution was like 1.5 inches. So it gets pretty fine because at that point you're like explicitly modeling aeration too. So you'll get those larger air bubbles within the flow domain.
Yeah, and again, those who are doing big flood models, a 1.5 inch, a couple of centimeters there for your mesh size, maybe just out of control for the types of applications that we're used to dealing with if you're a flood modeler. So maybe just hand off to everybody one by one, just doing closing thoughts. So Dennis, maybe over to you. Any closing comments before we knock off for the day?
Well, thanks for letting me present a very short, slightly different portrayal of what can be done with fun water. My expertise tends to be actually oil hydraulics, but it has been used in water simulations quite a bit. But yeah, thank you.
Awesome. Kurt, any final words?
Oh, yeah. Thanks for the opportunity. It's always great to kind of combine the passion for whitewater with professional modeling and engineering.
All right. Orly, any final statements?
No, thank you guys very much.
Excellent.
Somebody asked who's hiring, and somebody groundwater modeling.
Exactly. It might make our jobs, the rest of us, when we're doing some mundane work, might make that seem a little bit boring. But hey, we wanted to show you this just for fun. Next time around, in 1 month's time, we'll get back together and talk about how to actually compute the Froude number and how to do the computations that are maybe a little less fun than this, but still required to be able to have this sort of fun. Now, it looks like Shaw had to drop off as well, but yeah, I mean, this was all about people who take their passions into their careers. I was teaching courses in New Zealand, went out to Raglan where they're at, and they've set up, they're all surfers, and they've set up this office of hydraulic modelers with a window overlooking one of the longest surf breaks in the world, and they can just, when they see one coming and the conditions are right, they'll just go out there and surf. I mean, living life to the fullest. If we could all do that, we'd be better off. This is good for your mental health as well. Get out there, do some of these things. Get out there, get into the kayaking, into the canoeing, into the surfing. Ride some water slides. It's just, these are the things that people enjoy doing, and we've met some lucky people who are able to apply their passions in their careers. So thanks so much. You see on here on your slides some of the courses coming up. We would love to see you in those courses, and let us know with your feedback what you'd like to see more of in our future courses. So with that, we'll sign off for the day. We'll see you next time around with the Australian Water School. Goodbye.
Thanks for watching. Subscribe by clicking the link below and click on the notification bell to stay up to date with new releases. For the latest in significant, innovative and critical advances in water science, technology and management, subscribe now. To build your skills, enhance your technical knowledge and learn from leading experts in water, visit theaustralianwaterschool.com.au and discover our online training courses, both live and on demand.